Alright, welcome to today's episode of APOW Solutions. Today we're going through problem set 30 because last time I said I'm gonna start from the latest back. Now that we finished APOW 1 to 3, which doesn't have answers. So yeah, APOW 30. I'm only going to go through theory though because as you can see the time now is kind of late and I want to sleep. I'm tired. And also I am absolutely not a calculation person, so if we're lucky next week we'll do APOW 30 calc. If not, we'll just do APOW 29 theory. I'm sorry, but calc is not my thing, okay? It's not my thing. Anyway, question 1. Meme aside, what is the answer? First, to answer this, what is the Harvard's classification scheme? It's basically the OBA, FG, KM, all that. And now that we've listed the options out, you realize that I is not a valid spectral type. So it's C. Also, I said this problem. Oops. So I like how the OEIO, it's just nice, just nice I is not, but O and AR. But anyway, question 2. So what is this? It is an interacting galaxy. This is not really a thing. This is a thing, but both C and D are things, but C is an actual classification type. And some people might confuse irregulars, interactings, and peculiars. And honestly, this is also a peculiar, which is precisely why peculiar is not an option here. But what is a peculiar, and what makes it different from an irregular? Some people argue that peculiars are a subset of irregulars. All peculiars are irregular, but not all irregulars peculiar. And interacting galaxies could be even smaller subset between the irregulars. It's a peculiar, but whatever. Let's just consider them as disjoint subsets. Okay. So what makes a peculiar? Ring galaxies are basically peculiar, but since we found so many of them, we might as well call them ring galaxies. But technically they fall under peculiar galaxies because they're irregular in the sense that they're not lenticular, they're not elliptical, they're also not really a spiral. I can't draw a spiral, goddamn. So it's irregular. But wait, no, what am I saying? Okay, it's not the common types. It's not the regular tree, alright? So it is quote unquote irregular in that sense, but more importantly, it still has a shape. A ring galaxy still has a shape. You can't say that a ring galaxy looks irregular geometrically, even though it's not common, the main tree, So we call it peculiar because it does look like something, okay? It does look like something. So what is an irregular? Something like this would be irregular. You see those dwarf galaxies, they're kind of irregular galaxies because they're just like a mush, they don't look like anything. They're not really an oval, they're not really a circle, they're nothing. So that's irregular. Whereas peculiars actually look like something. Like how this looks like a rose, so it would actually fall under a peculiar if you were to argue about it. But regardless, it's an interacting galaxy because they're two galaxies and they're interacting, if you can't tell. And in fact, you see the blue stars here? This is likely a result, it's a starburst region, it's likely a result of them interacting and all, so yeah. And question 3, increasing brightness, should have underlined it below, whatever. The answer here is simply just C. If you can't tell, the hard part here in my opinion is Proxima Centauri versus Betelgeuse, but oh my god, why is there a double comma? Okay, anyway, you can tell it easily apart. To make it easier, which is why it's a question 3, we just didn't bother making Betelgeuse in front or whatever. And you could tell the rest because Sirius is the brightest star in the night sky, and Rigel is brighter than Betelgeuse. So if you know these 3, you basically can just fill in the blank and see that Proxima Centauri, or rather, see that C is the only option. So, yeah. Next one, which telescope is image taken by? It's the JWST-Y. Some people might get confused because if you count, there's 10, There's 1 pair, 2, 4, 6, 8, 10. But actually, I got scammed at first, by the way. This is dust, okay? This is dust. This is not the spike. The actual spike is just these 8. So that screams JWST for you because Hubble has 6. Chandra takes in X-rays, there's dust, so it can't be in X-rays. And Vera Rubin's a visual, but I don't know about Vera Rubin and the diffraction spikes on Vera Rubin, but But this A just screams JLST, so let's just roll with that. And also she does visual. Rare Ribbon's a visual. Which, it's also like a... I don't think Rare Ribbon is capable of zooming in so closely. But I could be wrong. I could be wrong. I could be wrong. Actually, let's find out. Oh yeah, I was looking at this earlier because I was confused as to why is there 10 spikes. But yeah, as you can see, this is dust. This is actually dust. Vera Rubin. Telescope. I should search images. What's Vera Rubin taking? What are you taking? Do you have diffraction spikes? Do you have diffraction spikes? Do you have diffraction spikes? Cross. Rubin's a cross. Very interesting cross, in fact. Split cross. Basically, it's not it. It's just not it. So yeah. This one would go to JBST. Also, these are pinwheel stars, which is very cool. With by pinwheel stars, it's like whatever this is called, which is, as I said, very cool. Okay, so you see this dust, right? So this is actually caused by, this is the Wolf Riot star, and in fact it's like a binary pair. And what happens is basically, as the stars orbit each other and stuff, they will create stable regions of cool dust, even though, you know, when you think Wolf Riot, you think like hot stellar wind and whatsoever, but because, you know, there's two stars, right, and then they both tug on the gas, so there will be this nice equilibrium where they're actually not really moving. And you know, because temperature is like a measure of kinetic energy, so like they're not really moving much, so they kind of cool, so they get to form these rings very nicely yearly. It's a bit like a tree ring, but not really. I mean, I don't take bio, so I'm not sure, but like intuitively I think it's a bit like a tree ring, which forms every like a regular amount of time. But yeah, pinwheel stars, check them out, please check them out. This one's Wolf Riot 140, I think, or 104. You search one of them and you'll find it. So yeah. Earth orbits move out. If it moves out, we'll have longer days, so duration of each season goes up. Therefore, C and D are out. If it's increased axial inclination, seasonal change becomes more extreme. So, yeah, A. It's A. Boop. Why the problematic? Because this is not true. The intensity of a pulsar really depends on a lot of factors, and the spin. In fact, they should. I'm not sure. Once again, I'm not sure, but I think they should be either on par or maybe slightly dimmer, according to intuition. But yeah, this one's not really the case, and this one has been discovered. They have been discovered, which is why it's a problem. That's precisely why it's a problem. It's more this, because pulsars they spin by having the strong, you know, magnetic field lines and shit direct electrons and charged particles, etc. So if you're having a slow rotation, right, where are you having all this energy come from? You know? So yeah, this one's another just memorization problem. It's this. It just is. I mean, if anything, Pluto is the second biggest, and then Eris is actually the biggest. I mean, that's the reason why Pluto got demoted, so like L. But yeah, and the other two you just kind of have to remember. You just kind of have to remember. There's like not really a choice. But it's a bit made easier because you realize that there's actually no other Pluto Aries, so like, do what you will. I mean, there's this, but like, Sirius is not it, okay? Sirius is not it. So like, yeah. Question 8 is here. Okay, blah blah blah. So John was running towards him, right? And there's significant dust. Running towards him means blue shifted. So it's either B or D. And there's significant dust means broad absorption lines. Because like the dust itself just absorbs, you know? It just does. Well, dust does what dust does. So yeah, it's D. I mean, if you want to know deeper, just Google dust and broad absorption lines. Basically, it's something to do with the different dust absorbing and then spreading it out and their own velocities and re-emissions, or like just not emit. Yeah, because when the... Okay, never mind, it's gonna be too complicated. Just Google it. Just Google it. Basically, there's a reason why dust causes broad absorption lines, and if I recall correctly, it's more or less due to each dust having different, like, absorption velocities relative to the to the light, or rather the wait a second, this question doesn't make sense. Jellyfish John is not emitting light. I like how it just assumed that Jellyfish John is emitting light. It is absolutely hilarious. But yeah, assuming that Jellyfish John is emitting light. I think people doing this question just assumed, because I just assumed. Yeah, anyway, question 9. What does it represent? It represents the exoplanet transit eclipse. Yeah, it just does. A detached binary, a contact binary wouldn't, cause like they're like this close, like they might as well be the same. This is not gonna happen. A detached binary shouldn't be, it should be more peakish, because look, there's a significant portion of time where it just remains completely covered, you know, like this is what happens. It's like going here, right? So after it gets like completely like it's here that it has this. So this part here is where it moves in, but like right after it moves into the star, it's all just here, and when it moves out, it's here. But look, it's only possible. This is only possible when you have a significant size difference or radius difference. So, which is more commonly observed in star and planet transitions than star-star binary eclipses. So like it's this. As for this makes no sense. Like why would the flux decrease? You know, why would it decrease? It won't. And also it's much more irregular and like crazy, I guess. So yeah, this one is D. And just like that, we're done with the theory. That's only 9 questions. Cool. And see y'all next week. See ya.